Hi, I'm Alina, and these are my friends, Sonia and Grace. We're all studying speech and hearing sciences at the University of Washington and working on a project together for a class on hearing science. Now, instead of writing a term paper to share our knowledge with our professor, we decided to find a way to share our knowledge with people who could actually use it. To that end, this is Why We Hear What We Hear, a crash course in sound and hearing for singers and other musicians. Well, before we start a journey through the auditory system, it might be helpful to know where we're going. Now, because I like to sing and coach choruses, my partners decided that we could use one of my favorite choruses, the Kitsap Chordsmen, as our example group. And here they are now. The Kitsap Chordsmen. Say hi, everybody!
Hi, everybody! Hi, everybody!
And here they are, under the direction of Mike Menifee, the Kitsap Chordsmen. During this video series, we'll briefly cover how sound is generated and how it travels through the air. We'll also learn how it's picked up, changed, and taken apart in the ear and put back together in the brain. These three concepts will provide the means to understand how you've been able to listen to my voice and tune out all these yahoos, how you can listen and follow just the melody, pick out that great bass part, and how the director can hear one guy singing the wrong note or at the wrong time in the midst of all of this. All these amazing abilities are easy for healthy ears, but as we age, most of us will lose some of our hearing ability and may even need hearing amplification. By the end of this video series, you'll know what types of auditory tasks are still easy if you lose some of your hearing, which aren't possible anymore, and how to use the strengths to overcome the weaknesses. Well, let's get started. Every sound we hear comes from vibrations. Vibrations of this desk, vibrations of the string, or of your vocal folds. Now imagine that sound coming out of your mouth. As your vocal folds vibrate, they bump into molecules in the air, pushing them closer together. Then those molecules bump into each other and bounce apart. As some move away, they bounce into others, and it happens over and over and over again. If we zoomed in on an incredibly tiny section of air while I'm talking, we might see something like what Sonia has drawn here. Now we can map out areas of high and low pressure traveling through the air in waves, sound waves. Now let's take a look at some real sound waves. E-ah, e-ah, ooh, ooh. Awesome! Now let's go back and watch that time wave form again. You can see that the areas where there was more sound energy, or the times where you heard louder sounds, that those made higher peaks in the time waveform. That means there was a higher amplitude at that moment. The pressure variations were bigger. Now let's compare some of these waveforms that we've mapped out from me and my dad. They look pretty similar, don't they? And they look a lot more complicated than the simple wave that Sonia drew earlier. That's because there's a lot of different frequencies in one vocal or instrumental or any kind of sound.
Now, we talk about frequencies in cycles per second, or hertz. In the simplest sound, a pure tone like you'd be tested with in the audiologist's office, it means how many high-pressure peaks there are in a single second. But most sounds are much more complex and have many harmonics. Musicians may know these sounds as the fundamental frequency and the overtones. Now, the pitch you hear is about cycles per second. That's the lowest frequency, and it's also the spacing between all the others. And the waveform is a combination of all of these frequencies. Just add it up. That's why these waveforms look so complicated, because they are. But we can take them apart by running frequency analysis in this computer program. And we can see that they're really just a bunch of simple waves added together. All sounds can be taken apart this way, even noisy ones that don't really have a clear pitch, like s, f, and sh. They just have sound energy blurred across whole frequency areas instead of separated out in complicated patterns. S is just higher and sh is just lower. So we've talked about how individual frequencies in a sound allow us to experience the pitch by the lowest frequency and the spacing that it sets up between them. But what else can these frequencies tell us? I ask you this, what's the difference between an ah and an oo at the same pitch? Or an oo from two different voices? Let's take a look.
When we compare the oos to the ahs in the spectrum, it's clear that the difference is the shape. It's about the amount of energy or amplitude at these different frequencies. That's what lets us experience a vowel. It's hard to see the differences when we compare my dad's oo to mine, but there are differences. You see, I have more high frequency components. We can tell the timbre of the voice or instrument by the shape of the whole spectrum. It's kind of cool to actually be able to see what you can so clearly hear. So now you understand both axes of the spectrum of sound, frequency and amplitude.
Now you may be asking yourself, how does this sound shaping happen? Well, try saying ooh-ah on the same pitch as was shown earlier. You try it. Ooh-ah. The pitch didn't change, so what did you change? The shape of your mouth, right? Ha! Think of it this way. You blow lots of frequencies into a bottle. It's like white noise. And a few get amplified and can be heard out here. You can change which ones by changing the shape of the bottle.
To wrap up this section, it's important to remember that the waveform shows pressure changes over time. If we look closely, we can see how often these pressure changes repeat and figure out what the pitch is. Here, it repeats this many times per second, this many hertz. We also see changes in the overall amplitude, like you can hear here. I kept the pitch the same, kept the vowel the same, changed the amplitude, or the amount of sound energy that you hear. If we pull out one moment in time, we can see the spectrum of sound. The shape these harmonics create shows differences in vowel, in timbre of voice, or in type or timbre of instrument. We also know information about the pitch of a sound because all of the pieces that belong to this sound will be multiples of the fundamental, 100, 200, 300, etc. Well, that's it for the very basics of sound. Now check out our next section, In Your Ears, where we'll explain how your ear breaks sounds apart, exactly like the computer program I showed you did. Only instead of fancy software, our ears use cells and weird, wobbly, gross tissues. Enjoy! See you then!